Hello, good morning, and welcome in the YouTube channel of SMD College of Engineering and Research Center, EOLA. Myself, Professor Harish Bhangare. We are discussing about the topics, various topics in the subject Basic Electrical Engineering of your first year engineering. So today's we'll discuss these topics like magnetic field of a straight wire, right hand rule, cross and dot conventions, electromagnets, and right hand grip rule. So one by one, we will discuss these things. In the last lecture, the introduction about the electromagnetic, the basic rules of the magnets that we studied. So now let us see what is the electromagnet. Now, with certain things where the electromagnetism is being used, that in your daily life we are watching it, we are observing it, and we are using these things daily. We are using in public places, lifts, escalators, even our house we are using fans, electric motors, pumps, then mixers, then turbines, drills, wheelchairs, car, windscreen, wiper, starter motors, windows and side mirrors. So like number of applications where the use of electromagnetism is there that we are observing and using in our day-to-day life, right? So even in blenders, food mixers, microwave ovens, hand power tools such as drills, sanders, routers, electric toothbrushes, shavers, everywhere we are using the applications of these things. Means in each application there is the motors, right? In mixer also, in food mixers also, blenders also, there is the electric motor, and electric motor is the best example of what you call electromagnetism. Okay. Now the magnetic field we already discussed. Now this magnetic field, lines of forces are there, and that magnetic lines of forces that have both direction as well as the magnitude. And that magnitude is nothing but the strength of the magnetic field, we can say, and they end at the poles. That magnetic field ends at the poles, means we can say in the other word, the magnetic field or lines of forces are originating from the north pole and will terminate to south pole, and internally again that magnetic lines of forces will travel from south pole to north pole, and externally in external environment surrounding the bar magnet travels from north to south pole, forming a closed loop. So there are such a number of closed loops are formed due to the magnetic lines of force. And also we know that these magnetic field can be tested by using a test dipole, and that test dipole is nothing but what you call it as a compass, right? By using the compass which is used for finding the direction, right? That same compass we can use here for finding the magnetic field, whether there is magnetic field or not surrounding a certain compass. Okay, so magnetic flux density, it is field strength, has a symbol B and its unit is Tesla. Now magnetic poles are always in pairs. So whenever a bar magnet, we consider that bar magnet has the two ends, and that two ends represents the two poles of the bar magnet, and the naming of that poles are north and south poles. Now these north and south poles, we can't separate it out, we can't isolate it out. If we break the bar magnet into n number of pieces, then there are the n number of pairs of north and south poles. Means we can't isolate these north and south poles. So this suggests that the magnetic effect of a permanent magnet comes from microscopic circulating electric current. Now the magnetizing and demagnetizing. Suppose I ask somebody to magnetize the given metal. So how can we magnetize it? So magnetizing is nothing but making a magnet. So we can make it by stroking, by using DC coil carrying current, by tapping while aligned with the Earth's field. And demagnetizing, we can easily demagnetize the magnet by simply dropping or bending randomly, by heating, by applying diminishing AC current. So in this way, we can magnetize and demagnetize. Now, what is magnetic induction? A permanent magnet can induce temporary magnetism in a soft magnetic material. This causes attraction but cannot cause repulsion. See, the permanent magnet can induce temporary magnetism, no doubt, in a soft magnetic material. If we rub the soft magnetic material on a permanent magnet, then in that soft material, the magnetism property may come that can attract certain things, metallic things like these pins are get attracted, and temporarily that magnetism will be induced in these pins. But they can only attract, but they can't repel. So that repulsion is not induced in that. Repulsion to test if any object is already magnetized. Now, what is the magnetic field of a straight wire? Now here is one straight conductor is there, straight wire, we can say it is a copper wire, you can say, and this copper wire is threaded out from a plain cardboard sheet. This is a one plain cardboard sheet, and this straight wire conductor is threaded out from this plain cardboard sheet. Now I allow the flow of the current through this straight conductor. So now as soon as this current will started to flow, that time what happened? No doubt, the current will flow from bottom to top. So that time certain magnetic field will be generated surrounding to this straight conductor. Now, the direction of this magnetic field can be found out by simply using the right hand thumb rule. So what is right hand thumb rule? So the right hand thumb rule is very simple. Here we have to use your right hand. So place the thumb in a direction of current, and the remaining fingers curl it on the conductor. So the thumb indicates the direction of the current, and the curved fingers indicate the direction of the magnetic field. So this is your simple right hand thumb rule, right? So we can state it like that: hold the current carrying conductor in the right hand such that thumb pointing in the direction of current and parallel to the conductor, then curved fingers gives the direction of the magnetic field or flux around it. So in the example here, it clearly shows this thumb is pointed towards the direction of the current, and these curved fingers indicate the direction of the magnetic field. So here on the card sheet, this is concentric circles. These are all the concentric circles that direction of the magnetic field, it is in the anti-clockwise direction, right? And thumb is pointing towards the direction of the current, means the current is flowing from bottom to top, means it's coming out, current is coming out upside from the page, right? Current is coming out from the paper. Okay, so this is your simple right hand rule, and that can be used here to identify the direction of the magnetic field surrounding the straight conductor. Now here again the straight conductor is shown, and here the two figures are shown, and in that what I have done, here the thumb indicates the direction of the current, it is upward, and in another figure the thumb direction of the current I reverse, that is downwards. So what happened, as soon as I changes or reverse the direction of the current, the direction of the magnetic lines of forces, or you can say magnetic field lines, also changes their direction. Here when the thumb directs towards the upside, that time the direction of the magnetic field lines is in anti-clockwise direction, and when it is downward, that time the direction of the magnetic lines is in a clockwise direction. So for this we can put a certain conventions, and that convention is called as dot and cross convention. And the dot and cross convention is used for the denoting the direction of the magnetic field and the current. So here For this figure, here is dot is there. A circle with a dot shows that the current is coming out from the paper. Here, in this figure, we indicates it by dot, and the dot indicates the current is coming out from the paper. Here, the current is coming out from the paper towards the direction of the thumb. Here, in this, the current is entering into the paper. Current is moving into the paper, right? Downward, right? So for this we will use the convention of a cross. So in detail, let us see this cross and dot convention. So here, in order to indicate the direction of the current flow, when looking at cross section of a wire, a cross and dot are used. Now a cross indicates the current is going into the page, entering into the page, as though you were watching the flashing feathers of an arrow as it travels away from you. It is just like a arrow, right? And that arrow is traveling away from you. While dot indicates the current is coming out of the page. Here the dot indicates this is a dot. The dot indicates current is coming out from the page, as though you were watching the point of an arrow as it comes towards you. एक एरो को छोड़ दिए है और एरो आपकी तरफ आ रहा है, और एरो हेड जो इंडिकेट कर रहा है दैट इज द डॉट बिकॉज इट इज कमिंग टुवर्ड्स यू, व्हाइल क्रॉस इज द फीदर्स ऑफ द एरो. आपने एरो छोड़ दिया है और एरो का जो टर्मिनल है, एंड टर्मिनल है, वो आपकी तरफ है, आपसे दूर जा रहा है, दैट इज इंडिकेटेड बाय क्रॉस. So in this way, the dot and cross convention is used for indicating the direction of current, right? When looking at a cross section of a wire, so that cross and dots are always mentioned there. Now, what is the magnetic effect of electric current? Now, in a simple language, what is electromagnets? So we already know that an electric current has the ability to produce a magnetic field in a plane perpendicular to the direction of the current flow. अभी हमने देखा एक प्लेन कार्ड शीट हमने ली, उसके अंदर हमने एक कंडक्टर वायर थ्रेड किया और वायर में से करंट हमने अलाउ किया. So what happened? We observe the magnetic lines of forces surrounding to that wire. Means it is the effect of what? Electric current flowing through that straight wire conductor, right? And that effect is nothing but, we can say it is an electromagnet. So this electromagnet uses this principle. Now, in a simple language, an electromagnet can be defined as a magnet which functions on electricity. Now, permanent magnet we have already studied. Permanent magnet, all time it has the magnetic effect. All the time certain magnetic lines of forces are there surrounding to that. In magnetic influence is there around that bar magnet or permanent magnet. But electromagnet is one which functions or which works only in presence of electricity. So unlike a permanent magnet, the strength of the electromagnet can be changed. Strength of the electromagnet can be changed by changing the amount of electric current that flows through it. No doubt, the strength of the magnetic field depends on how much electricity you are passing through that coil, right? That will define the strength. If the current flow is cut, the property of magnetism ceases to exist. Mean this will exist only in presence of electricity. So what is electromagnet? Electromagnets are made out of a coil of wire, and that wire curved in a series. So this is more effective in producing a magnetic field than just a wire running straight. So this effect can be strengthened by winding a wire tightly around a powerful core made of magnetic material such as iron. So here this figure shows the wire is wound on this core material, right? And we allow to flow the current through this coil. So only if you use a straight wire conductor, that also shows you certain magnetic effect, but the strength is less. To have more strength, such a coil is being used, and that electromagnet is a simple. When a coil or a conductor carries a current, it produces the magnetic flux around it. Then it starts behaving as a magnet, Such a current carrying coil or conductor is called an electromagnet. So this is due to the magnetic effect of an electric current. So it is nothing but an electromagnet, and this will behave as a magnet only when the current passes through this coil. As soon as I cut this current, it seizes out the property of magnetism. Now the magnetic field of a solenoid. So the right hand grip rule, it wraps. We have studied the right hand thumb rule, very similar to that right hand thumb rule. Right hand grip rule is there. Now this that right hand thumb rule is for a straight wire conductor, while this right hand grip rule is for a solenoid coil. It is for a coil, the coil wound on a core. So according to right hand grip rule, wrap the fingers around the solenoid in a direction of the current. Then whatever the direction of the thumb, that thumb indicate the end pole, that is the north pole. That thumb indicates the direction of the north pole, means your north pole is towards the thumb. And when you are the north pole, we identified, we got the direction of the magnetic lines of forces, because from north pole itself, your magnetic lines of forces comes out, right? So in this way, here is the direction of this magnetic lines of force or magnetic field, you can say, right? So thumb indicates the direction of the magnetic field, right? And that magnetic lines of forces coming back at the south pole. So this is your right hand grip rule, that is wrap the fingers around solenoid in a direction of current, then the thumb indicates the north pole. Now note the similarity in these two figures. This is a permanent magnet. It is an electromagnet. In this electromagnet, this coil is wound. N number of coil turns may be there. This current I is entering in this direction, and here is leaving, right? So it is a permanent magnet. Now from this permanent magnet, this north pole, from this north pole, this magnetic lines of forces coming out and emerges to south pole. Here also this electromagnet, this is the north pole, this is south pole, and electromagnet from it lines of magnetic forces comes out and will again goes to the south pole. So this is the similarity, that is in both permanent as well as north pole, sorry, in electromagnet, there exist north and south poles, and the north pole from both magnetic lines of forces comes out and that enters into the south pole. Now the difference in both is that for this permanent magnet, these lines of forces are permanently, there is the influence of magnetic field all the time. But here in case of electromagnet, in presence of the electric current only, these lines of forces exist, otherwise it ceases out. Now the stronger electromagnet, when we can give the strength to the electromagnet, suppose the length of the solenoid is L, it is a fixed, then use an iron or steam core so that its permeability can be increased. So increase the current strength, I increase wraps, that is number of turns on the solenoid, that will strengthen your electromagnet, right? And here is the formula for the electromagnet, for the magnetic field is B is equal to mu Ni upon L. Mu is your permeability of the material, N is number of turns on a solenoid, I is the current, magnitude of the current flowing through that coil, and L is the length, right? So if I increase number of turns, strength of magnetic field increases. If I increase magnitude of the current, my magnetic field increases, right? So in this way, you can strengthen the magnetic field of an electromagnet. Now here we are using this electromagnet. What are the uses? So in loudspeaker, we are using the electromagnet. Moving coil microphone, electromagnet is there. Motors of various designs, electric bells, buzzers, in that electromagnet is there. Moving coil galvanometer, that is in ammeter, electromagnet is there. Relays, electromagnet is there. So number of applications of the electromagnets are there. So this is all about the electromagnets and how to find the direction of the magnetic lines of forces depending on the direction of the current flowing through a coil, straight wire conductor, as well as the solenoid. So for today, it is sufficient. So in the next lecture, we'll discuss the next topic. Till then, thank you.